Hi everyone. So today I'm going to go over a different final exam. I'll try to go faster this time. Okay. Ooh, excuse me. Answer only questions, right? Okay. Give an example of, and so I am not promising that our exam is going to look like this. I don't know what our exam is going to look like, but anyway, these are some examples of questions that could be asked. Give an example of two non-empty sets C and D so that the collection, curly T equaling that thing, is a partition of the rationals. Interesting. What and B is that thing? Oh, so I just have to pick out who C and D are. Okay. So I'm going to pick a different way to write B. B, I'm going to also write it as the intersection of Q and negative infinity, -7, but not including -7. Okay, well, I'm just going to pick C. So rationals intersected with -7 inclusion to 7, including 7. And then I'll pick D to be the rationals intersected with. Now we start at 19 and we go to infinity. So their intersections with each other are all going to be empty sets individually. And their union together should equal all the reals. Okay, all the rationals, sorry, that's what I meant. Cool. Give an example of a function. Excuse me, sorry. That's injective and not surjective. I think we had this last time. Maybe I could think of something new. Okay. Wait, let's look at the last one that I did. Was that also injective, not surjective? Because then I could switch them and say surjective and not injective. Yeah, it is the same. Okay. So let's say is not injective and is surjective. Okay, so I'm going to change the question. Okay, so is not injective but is surjective. Well, oh right, these ones are a lot harder, aren't they? Well, I could do like a cubic. So, how do we do these? X plus -1 times x minus 1 times x. Yeah, because that's going to look like... Wrong. I couldn't remember if it comes from the bottom or from the top. But this is what my thing looks like. Oh, my laundry's done. Okay, so as you can see, like, sure, it's not a huge bump or whatever, but it does not pass the 1-to-1 test. Oh, we could just look at the 0. Oh, the package was delivered. That's nice. So this is surjective because it hits everything on the y-axis, but it is not injective because x equaling 0 and x equaling 1 both send this to 0. Okay. All right, find 3 numbers such that GCD... Oh, interesting. Okay. But GCD of BC and does not equal... Okay. So these are the same. Okay, so let's just try something. So like A, B, and C. Okay, so my first thought when I was looking at this was I said, why don't I just let 2 of them equal each other? But then that would cause problems with this next part. So they all, I think, need to be different. So my thought is like 6, 3, and 2. Ooh, okay. C is 6, 3, and 2. Let's try it. So I'm not guaranteeing that this is right. Alright, so A, B would be 3, 2, so that'd be 1. 3, 6, that'd be 2. GCD of 2, 6. Oh yeah, that doesn't work. Okay. What if we do... So it has... Okay, wait. Alright, now let's... Instead of just guessing, let's do this systematically. Okay. So what needs to happen is that A and C need to either have a lack of a divisor that B and C have, or it has to have an additional divisor. Why don't we try C is like 12? B could be... Oh, I'm making this more complicated than I think it needs to be. B could be 1 and A could just be like 3 or something, right? 3, 1, so that would just be 1. This is what, 3, 12, so that's 3. And then BC, that's going to be 1, 12. Yeah, I made it more complicated than it needs to be. Okay. There we go. Hi everyone. Okay, so we started that last final, but then I realized it was very, very similar to the other one that I've already posted on my YouTube. So I kind of Frankenstein this final out of other past exams and things. So I think that we'll cover major points, but it's a little bit of a hodgepodge. And that is a reference to Mary Shelley's Frankenstein. And Frankenstein is the doctor who made a person, or what do they call him, creature, out of different body parts. Anyway, you thought you came to math class? Switch it around, you know? Okay. For each of the following sets, find the stated index union intersection. So I don't think I have to do a proof for this, or else it'll definitely be worth more points. Alright, so let's see. So I often tell you to do maybe like the first few iterations. So what do we get? We get 7 minus 1, 7 plus 1, A2, 7 minus a half, 7 plus a half, and I'll keep going on like that. Okay, well, so this... So let's represent them on a number line. Okay, let's see. So let's call this 7 maybe. So 7 plus 1, well, indeed that is 8. 7 minus 1, that is 6. So maybe I'll call A1 this pink color. So I'm going to go from here to here. Okay, and maybe let's call this A2 blue. Well, 7 minus a half, that would be 6.5, and 7.5, and everything in between. Okay, so, and then they're just going to keep getting smaller and smaller in here, right? So, what ends up happening is that the intersection keeps chopping off these bits, because remember, the intersection only cares about where they all overlap. So, the intersection is going to be kind of like... where this is all heading. Well, it's actually heading to 7, 7, isn't it? Now we need to think about, okay, but is 7 included or is it not included? Well, 7 is going to be in every single set because we can't actually minus 0, right? So n goes to infinity, but we can't just like plug that in and be like, oh yeah, look, so we do end up minusing by 0. So the intersection of n, that's going to be the set just including 7. But the union, actually we take that same information that they keep getting smaller and we say, okay, well the union is actually just the first set. So the union is A1, and who is that? That is 6 to 8, open brackets. Okay, boom, roasted. All right, question 1 in quotes. Negate each of the following statements. For each of them, state whether the original or negated statement is true. Give a one-sentence justification. So I'm going to say that out loud, the justification. So negation. So, all right, let's see. So if A, B satisfy that, then this. Remember, negation of an if-then statement is an and statement. So we want A comma B isn't real such that A squared. And so I'm changing some of the words, and that's fine. It's just that they're logically equivalent. And not the other thing. So what's the negation of that? Will be A is not equal to 0, or b is not equal to 0. Okay, so let's see. Here's how you could think about it. You could think about it like p implies q and r. Okay, so then the negation of this whole thing is p and the negation of q and r. But what is that? That is actually p and negative q or negation of r. Okay, and so that's why I wrote it like I did. Okay, now I'm gonna erase this, so be warned, or pause. Okay, so let's see. So which one is true? Yes, the first, so the original is true. OG, true. And how you could think about it is any real number squared is always positive unless it's 0. Then it's just going to be 0 again. Okay? So we can't have them cancel each other out somehow, because if we solve for this, we would get, when does this happen? Well, it can never, b squared can never be negative, so it would have to be that b squared is 0. Or sorry, a squared can never be negative, so it would have to be that a squared is 0, b squared 0, boom, roasted. Okay. All right, so remember, you would have to actually write that if this was an exam you were taking, but I am not. I don't know if you guys could hear my rabbit sneezing, but it's the cutest darn thing. Okay, I think this is part of just like the beginning. Is it? So m is even. Oh, no, that is part of it. Sorry. Okay, so I'm just gonna call it n, the negation. There exists an m and an n in the integers such that, and then we would negate this thing, which is an and statement. M even or n even and m plus n odd. Well, yes, there does, because all it needs to be is an or. So if m is even and n is odd, so like 2, so m equals 2 and n equals 1, let's say, m plus n equals 3 odd. Alright, so there does exist one. So this one is true. I'm running out of space. Alright, so maybe I can start over here. Alright, so the negation of there exists a y and z for all that. Okay. Alright, so for all y and z, there exists an x and z such that x plus y is not equal to 0. Oh, sorry, this isn't the negation. Yeah, no, the negation is true. Yeah. So, so two cases. So if y equals 0, choose x not equal to 0. B, if y not equal to 0, choose x equals 0. Because remember, this exists thing, that means we get to just pick one. Okay, then we're done. So this one's true. Alright, lastly, the negation. What do we have here? Oh, sorry, I lost my spot. Okay. Exists an x in the integers such that for all y in the integers. No, this one's false for sure. So OG true. Wait, is this the same? Oh, wait. Yeah, so it's almost the negation of this one. This one and the original for D are almost the same. It's just it's the equaling 0 thing. So so OG true. So part A once again. So if x equals 0, choose y equals 0. Remember, I'm talking about the original statement D over there. So B, if x not equal to 0, choose y to equal negative x. Since x is an integer, then negative x an integer. Boom. Okay, so that would be my explanation for that. Let me figure out how to make more space. Also, I didn't think to mention this, but But you can totally try these on your own, and I actually would even encourage that. Okay, so that's nice of them. We're just showing that they're inclusion. We're not showing strict. Okay, so how am I going to do that? Well, first, I just since we're talking about x's, maybe I'll pick something else. Let maybe y. Oh, I'm going to call this set A and this set B because I don't want to have to write that every time. So let y be in A, then there exists maybe like a k in the rationals such that, this is distracting me, okay, such that 2 to the k equals y. Interesting. Okay. Well, what do I want? I want y to be in B. Well, what does that mean for y to be in B? Then there exists, I don't know, maybe I'll say some L in the rationals such that 2 to the L equals y. Okay, well, if I have, oh no, not 2, sorry, that's the point. 8 to the L. Well, if I have 8 to the L equaling 2, oh my gosh, equaling 2 to the k, what in the heck does that mean? Well, I can actually write 8 as 2 to the 3rd, right? And this whole thing's raised to the L. Well, that, we get to multiply those two together. Ah, okay, so we would just get 3L equals K. So that's kind of the formula that we're thinking about. Well, okay, sorry, wait. Even more than that, because we're kind of trying to figure out what L is going to be. So we get that. And that's totally allowed. You might be saying, Danica, usually you freak out when you divide something. Well, we're in the rational, so we can divide by integers. That's okay. Okay? So now I'm going to say consider... Oh, wait, no. No, how I had it before, that was good. Because I already have my k. Okay. Consider... Oh, yeah, I'm sorry. I keep getting myself confused. All right. Consider y... 2 to the... So y equals 2 to the... I'm sorry, I'm struggling how to write this. Okay. How about we'll do this, okay? Well, that's the same as 2 to the 3rd to the k over 3. Well, that's 8 to the k over 3. Which is in B since k is in the rationals. So k divided by 3 is in the rationals since 3 is an integer. And the rationals closed under integer division. Okay, so, I mean, I'm not so sure how much explanation you need to give. You could also rewrite k as like k equals a over b, where a and b are integers, you know, and then you could say like, okay, well, k over 3, that's going to be a over 3b, which is definitely in the rationals because 3b is an integer. Actually, that's probably a better way. At least at your level, that's a better way to write it. Okay. Therefore, y is in b. Sorry, I'm going to do bad notation right now. So then a is a subset of b. Boom, roasted. So remember, if I were trying to show a strict subset, I'd have to pick something out of b that was not an a. Although, I think that these are probably going to be equal sets. I don't know. You could prove that. You have all the tools you need. All right, let me space this out again. Okay, so assume that m is an integer and prove that at least one of those is divisible by 4. Okay. Whew. So I'm gonna rewrite this. Show 4 divides m minus 3. Sorry, sometimes I rewrite stuff in my own handwriting just because it's easier for me to see my own handwriting. What do they call it? Ducks do it. It's like image search or something. I remember learning that in AP biology like 100 years ago. All right. So let's see. Proof. What am I probably going to use? Well, I'm probably going to use division lemma. So by division lemma, there exists a unique k nar in the integers such that m equals 4k plus r. And what do we know about r? We know that so we're allowed to do this since m is an integer. And 4 is also an integer, but that I think we can go without saying. So r equals 0, 1, 2, or 3. Because remember, this is a strict inequality. Okay, so now I'm just going to go through all my different options, and I'm not just going to show that it divides. So I'm going to show that it divides one of these. That 4 divides. That 4 divides one of these. Okay. All right, so let's try it. So call it case A or something. If m equals 4k plus 0, then, well, in fact, 4 divides m, but that's not what we're trying to show. Okay, so maybe we should add something to m that is also divisible by 4. Oops. Like this thing right here. Okay, whoops. So that's not very helpful, what I just wrote, so maybe I'll erase that. Then m plus 4 equals 4 times k plus 1. So 4 divides m plus 4. B. If m equals 4k plus 1, so I want to add something to 1 or subtract, that's also an option, such that I can divide by 4. Well, 7 plus 1, that's 8. That's definitely divisible by 4. Then m plus 7 equals 4k plus 8, which is 4 times k plus 2. So 4 divides m plus 7. C. If m equals 4k plus 2. Well, I think I'm going to use the plus 2 one. 4k plus 1. So 4 divides m plus 2. And then lastly, you probably guessed it, we're going to use the minus 3. Then m minus 3 equals 4k. You didn't even have to do anything fancy with that one. And then I would write my conclusion. Therefore, for any m in the integers, 4 divides m plus 4, 4 divides m plus 7, 4 divides m plus 2, oops, or 4 divides m minus 3. So one of those things has to happen. Maybe more than one of those things happens, probably not. But all set. Let me figure out my spacing. So use the definition of convergence. Oh my gosh. Yeah, give us a lot of space. I don't know how much this is going to be. Okay. So, use the definition of convergence. That is the n epsilon argument to prove that thing. Okay, so they're saying we want to prove that. All right. So part A, proof. So you'll definitely want to write like definition of convergence somewhere. That alone could get you some points. Okay, choose epsilon greater than 0. Great. Now I'm going to immediately jump over into La La Land and we'll do some scratch. So I want to make sure that, so I'm going to call this thing an. Okay, so I want an minus 3, because remember that's my L, to be less than epsilon. Okay, I want to figure out someone that I get this. So maybe I'll say like a sub capital N, because that's usually what we use. I don't know. We're in La La Land. We can do a lot of things. All right, so let's first just consider this. So what is that? 9n squared plus 2n plus 5 all over 3n squared plus 11 minus 3. All right, so common denominator. I know it looks hideous, but we got to do what we got to do. All right. What do we get? 9n squared plus 2n plus 5 minus 9n squared minus 33 all over 3n squared plus 11. absolute value of this thing. All right, so let's simplify. These cancel. So we have 2n, oh boy, minus 28, 3n squared plus 11. Okay, all right. Okay, well, we could get bigger. And remember, we don't want to get too big too fast that all of a sudden we are bigger than epsilon or something, or the epsilon's not allowed to be as tiny as it wants to be. Let's see, what could make us bigger? And then this is where it's tricky too. So we want it to be, even when n is humongous, we want this to be less than epsilon. So maybe we say like n at least 14, and we write that as a note to ourselves so that we can, so we remember to write it in our proof as well. Okay, so then that gives us that this version is positive. Because remember, if like n was like 1 or something, we would have to write 28 minus 2n. Okay, so let's see. Now to get this bigger, we could get rid of... Oh, sweet. Okay, so we can get rid of the thing on top, right? Because the bigger the numerator, the bigger the whole number. And we can get rid of this thing on the bottom, because the smaller the denominator, the bigger the number. All right, let's see. Does that make us too big? I don't think so, because we still have n stuff happening. So we get 2 over 3n. 2 over 3 epsilon. Oh, man. Yikes. Okay. What if, okay. Yeah, we'll just leave it like that. That's fine. Everything's fine. All right. By AP, since 2 over 3 epsilon is in the reals, there exists a natural number n such that 2 over 3 epsilon is less than capital N. Oh, I don't know why I find that so funny. Okay, so, all right. Now, what do we want to do? So then for all and the naturals such that... Oh, wait! I almost forgot this piece. So there exists an n in the naturals such that n is bigger than that thing and capital N is bigger than or equal to 14. Right, is that what I said? Yep. Then for all the natural such that capital N is less than or equal to little n, we have, so now I start with a sub n minus L. What is that? Well, that is 9n squared plus 2n plus, oh wait, I can skip some steps because of, okay, this is 2, I don't even need the absolute values anymore, 2n minus 28 over 3n squared plus 11 by scratch. Okay. And then I can say this is less than 2n over 3n cubed. Oh, squared. I was like, oh, did I just do the whole thing wrong? Which is less than 2 over 3 capital N. Because remember, the smaller that we make the denominator, the bigger that we make the whole number. Okay. Oh, I'm just realizing I could have gotten rid of that 3. Oh, I'm so silly. Because I didn't care about the 2. Anyway, all right. So this is smaller than, so I can make it even smaller by doing, I'm not even sure if I ever showed this in class. So those 2 cancel. And then what do? You do 2 times epsilon over 2. This is epsilon. So the epsilon, oops, epsilon is bigger than a sub n minus L for all n equal to capital N in the naturals. Therefore, a sub n converges. Woohoo! Okay, craziness. Next, express keys of volume interval. Okay, so our first one. So what would we have? We would have like negative 11 to 11. And then we get to keep going forever and ever. So this is the whole real line. B, this is not the whole real line. This is -11 to 11. And you want to think to yourself, so are they closed or open? Well, -11 and 11 are in every single set. This one, this is intersection. Okay, we need to pay attention to that. So what do we start with? We start with 4 to 9. And then we keep getting closer and closer and closer to 5 and 8. 8 from the right and 5 from the left. So it's 5 and 8, and it is inclusion because we get to keep both of them. Well, both of them are in every set. But this one though, oh wait, they flipped the plus or minus on us. Okay. So we start with 6, and we slowly approach 5. So we get 5 not included because 5's not in any of the sets. And then for this one, we start at 6 and we slowly approach 8, but we never touch 8. Cool. All right. Oh, I didn't give myself any room on this one. Okay. Assume X is there. Prove the following statement. Oh, yeah, this was going to be like my, I was going to show a contrapositive proof on this one. So I'm going to do contrapositive. Because last time I showed contradiction. Contrapositive. Alright, what is the contrapositive of this thing? Well, remember we flip-flop them and we negate both of them. So if x odd, then x squared plus 3x plus 5. Okay. So I want to prove this contrapositive. Proof. Bless you, ma'am. Okay. Assume x odd. Then there exists some k in the integer such that, x equals 2k plus 1. Okay. X squared plus 3x plus 5. So let's go through. 2k plus 1 squared plus 3 times 2k plus 1 plus 5. 4k squared plus 4k. Oh my gosh. Plus 4k plus 1 plus 6k plus 3 plus 5. Okay, 8, 9. So we get 9, 10k. So I want to show that this thing is even. Oh boy, what? Did I do something wrong? Okay, so I think somebody like changed it on the exam, or maybe I did make a mistake. I know you all are really good at emailing me when I make mistakes, but but I do appreciate it. Okay, so let's change it to 8 and 3. So let's see. This just changes to 8, 3. 8 and 3. 8 and 3. 16 plus 8 plus 3. Yes, okay, that should work. Woo! I'm nervous. 20k plus excuse me, 12. All right, all those things are divisible by 2. Yeehaw! This is in the integers. So then x squared plus 8x plus 3 even. Therefore, the contrapositive is true. Because notice that the contrapositive of the contrapositive is the original statement. So let's state it. It's that if x squared plus 8x plus 3, if that is odd, right, then x even. Boom, roasted. All right. So let's see. Question 4. Use mathematical induction. So that just means induction. All right. So what is that? That is 0 Well, 7 definitely divides 0. Check. Boom, roasted. Alright, so base case, induction hypothesis, inductive hypothesis. I think either one is fine. It might come down to English thing, hypothesis, I don't know. Okay, so for K and the naturals, because we are working with the naturals here, assume 7 divides 2, 3k minus 7k. Inductive step. So we could talk about what we want, or maybe what we could do, so we can elaborate more on this. So then what happens? 2 to 3k minus 7k minus 1 equals 7 times L for L in the integers somewhere. Okay, so now let's consider 2 to 3k plus 1 minus 7 k plus 1 minus 1. Let's try to make this thing look like what we had before. What we have up here, I guess is what I mean. Or at least something similar to this. Or what could we do to it to make it look like that? Well, let's see. So we have 2 times 2 to the 3k. Oh, wait, sorry. 2 to the third times that. Yeah. Distribution is very important. Okay. Minus 7k minus 7 minus 1. So really that's like minus 8. Okay. Alright. Well, I could... Ooh, okay. Well, I could change around this formula up here. I could say 2 to 3k equals 7l plus 7k plus 1. That might be something, I'm not sure. 7l plus 7k plus 1 minus 7k minus 8. And maybe I should just change this to 8. Is this still not true? Oh boy. Okay, well, let's just see what happens. So what do we want to show? We want to show that it's divisible by 7. So we want to be able to pull 7 out of everything. Well, oh yeah, okay, so we're done. Okay, sorry. Just had a brain lag or whatever, the loading symbol. Cancel. And then we can pull out a 7. Oops. And it's okay that we still have these k's in here, because k we know is an integer. Okay? Therefore, k divides, 7. 7 divides this whole thing. Therefore, by induction, and remember to mention induction in your conclusion. Therefore, by induction, 7 divides 2 to 3n minus 7 times n plus minus 1 for all n greater than 0 or just the naturals. Oh my gosh, I just remembered. I did do that wrong. Oh my goodness. Okay. So this is still true. It is for non-negative. I am so silly. It's just too late at night for me to be doing this. So watch. I totally made a huge blooper. 2 to the 0 is 1. How crazy is that? So when n equals 0 and when n equals 1, we both get the 0. Okay, so now, okay, and I never divide by k, so that's fine. We don't have to worry about that. And then just add. I think I was just on guard because the last question had a little blooper in it. Okay. 15. Well, let's just move that down. Man, I was trying to make this one shorter, but I think I don't even think that your exam would have this many questions. I'm not exactly sure. Combined with the other video, I'm not sure. All right. Ooh, are they a partition of each other? Actually, I'm not sure if this could be asked on your final. You would have to ask your instructor, but I'm not a part of making the finals. Okay. So I want A intersect B to be the empty set and A union B to equal R. Okay, so maybe let's start with part 1. So A intersect B, how about I'll say like if X is in here, and so I want to show that X doesn't exist, then X is in A and X is in B. Because remember how you show this equality is you want to show this way and this way. But this one is just always true. The empty set's always a subset of any set, including itself. Okay. So then X is in A and X is in B. So X is in A means X squared is bigger than 1. X is in B means X squared is less than or equal to 1. Well, maybe how I could say it is like X squared is either greater than 1 or less than or equal to 1, but never both. Therefore, there exists no X. And A intersect B is a subset of the empty set. And then we would say the empty set is a subset of A intersect B. I don't know, by definition? I'm not sure. Therefore, the empty set equals A intersect B. All right, part B. Oh, I call it I. So I want to check is it equal to all the reals? Well, something that we can probably figure out quickly is it's not going to be, because we can pick out like a negative number. So choose or consider -1 in the reals. Does there exist X in A or X in B such that X squared? Oh wait, so we would only care about B because B talks about things that are less than 1. Yeah. So X squared equals -1. No, not for the reals. Not in the reals. Because remember, B is only pulling from the reals. So if you all have heard of imaginary numbers, you might know what would work for this. Therefore, R does not equal A union B. This means that AB is not a partition. Of the reals. Boom, roasted. Okay, well that concludes it. Good luck on all your exams and happy holidays.